Welcome to the channel. My name is Charles Carroll. This video is part of the PIWCWG series, where we explore how structure, information, and persistence shape the universe, layer by layer, using careful reasoning and established physics as our guide. In this episode, we explore a question that sits at the boundary between cosmology and long-term structure. Can directional bias survive across cosmic cycles? This is episode 19, Directional Pulse Universe. Modern cosmology often assumes that, on the largest scales, the universe is statistically uniform and directionless. This assumption, called isotropy, has served physics well. But it is an assumption, not a law. It holds as long as deviations are small enough to ignore or average away. The directional pulse universe asks whether that averaging is always complete. If the universe undergoes cyclic or quasi-cyclic phases, expansion, dilution, restructuring, and renewal, then the question becomes whether each cycle fully resets directional information or whether small asymmetries can persist from one pulse to the next. This is not a claim that the universe has a preferred direction in the everyday sense. It is a question about memory under repetition. In many physical systems, cycles do not erase all history, they filter it. Consider waves traveling through a medium. If the medium is perfectly symmetric, waves average out. But if the medium has even a slight bias, a grain, a gradient, a residual strain, then repeated pulses reinforce certain directions over time. The bias does not need to be strong. It only needs to persist. In the PIWCWG framework, persistence is never absolute. It is selective. Information survives only if it is carried forward through constraints. A directional pulse universe proposes that early cycle asymmetries, however small, may leave imprints that are not fully erased by later expansion or thermalization. This does not violate known physics. General relativity allows anisotropic solutions. Quantum fields can carry directional correlations. Inflation smooths many irregularities, but it does not guarantee perfect erasure of all phase information, especially at the largest scales. The key question is not whether symmetry exists, but how perfect it really is. If directional bias survives across cycles, it would not appear as a sharp arrow or axis. It would appear statistically as slight anisotropies, preferred alignments, or low-level correlations that refuse to disappear even as datasets grow. Importantly, this framework does not predict dramatic effects everywhere. Persistence filtering implies subtlety. Directional memory would be strongest where dissipation is weakest and where cosmic scales approach horizon limits, places where averaging is least effective. This reframes how we interpret certain observational tensions. Instead of treating every anomaly as error or coincidence, the directional pulse hypothesis asks whether some residual structure is the expected outcome of a universe that pulses rather than resets. Crucially, this idea is falsifiable. A directional pulse universe would predict consistent, scale-dependent directional correlations across independent probes, not just in one dataset, but across multiple observational channels. If improved measurements continue to wash these signals away, the hypothesis fails. That failure would be informative. In the PIWCWG view, persistence does not demand survival. It only demands the possibility of carry-through. Directional bias either survives filtering or it does not. Nature decides. This episode is therefore not a conclusion. It is a boundary question, one that sits between cosmology as we practice it now and cosmology as a long memory system operating across vast temporal cycles. If the universe pulses, the deepest question is not how big each pulse is, but what survives between them. This was episode 19, Directional Pulse Universe, and the question of how directional bias might survive across cosmic cycles. If you made it to the end, thank you for taking the time to listen carefully. These ideas are meant to be considered slowly because they live at the limits of what observation can currently test. Thanks for listening. Join us next episode. Episode 20, Hubble Note, Redshift Ledger.